So at the heart of this lesson, I'll call it mathematical efficiency, but really it might be mathematical laziness. If you and I were asked to multiply out x plus y to the fourth, I think you would realize fairly quickly that as you multiplied these two items out, you'd get a trinomial. Well, if you multiplied it by that, you'd get something much larger, more pieces and more parts. And when you multiplied it by this, you'd get more pieces, more parts, and this would just be a huge mess. So we're going to find a way to do this much faster and easier. All right? And it follows a very cool pattern called the Pascal's triangle. Watch. So like all things in mathematics, we need a pattern. So if I take the binomial x plus y and raise it to the 0 power, anything equals 1. If I raise it to the power of 1, it's just itself, 1x, 1y. If I do this guy here, let's do the math of this. X times x is x squared, x times y, another x times y, and another y times y. And what we get is 1x squared plus 2xy plus 1y squared. Whew! Just that was a lot of work. Now, I'm going to take a shortcut. And the next one, I want to multiply this times this. Now, the shortcut I'm going to take is that answer, this first answer here, is right above. I just did that math. So let's spare us a little bit of work. But already I am feeling a little overwhelmed by the amount of work. So let's multiply this out. You ready? X times each of those. That would be 1x cubed plus 2x squared y's plus 1xy squared. Now let's multiply y times each of those. That would be 1y x squared y plus 2xy squareds plus 1y cubed. Do you see what's happening? Now, I actually, before I leave this, I want to summarize these together because there are some like terms. Can we find them? So this has got an x squared and a y. Do we have another one? Yes, we do. We got another one of those. And do we have an xy squared? There's an xy squared and an xy squared. So I'm running out of some room, but let's do it. It would be 1x cubed plus 3x squared y's plus 3xy squareds, and it would be a 1y cubed. Oh my heck. Basically, I've made a mess, and you're like, what's this guy doing? So let's see if I can show you the beginning of the pattern before I have to erase this. Watch. There's something going on here. We got a 1. Let me put that right here. In the next case, we got a 1 and a 1. Let's put that over here. In the next case, when we were done, we had a 1, a 2, and a 1. All right, let's put that over here. And in the next case, we had a 1, 3, 3, and a 1. A 1, 3, 3, and a 1. Now, you may not see what's going on, but there is this kind of cool little pyramid happening. We see a pattern of the 1s along the edge. We see something happening in the middle. Now, let me begin to help you with the middle. This is so cool. Pay attention here. Where does this 2 come from? Do you see how it's got a 1 and a 1 above it? 1 and 1 make 2. Let's find out where this 3 comes from. A 1 and a 2 make a 3. A 2 and a 1 make a 3. Do you know the next line? I do. 1, 4, 6, 4, 1. Whoa, crazy. Let's clean this up and let's talk about it. So in a much better readable form than that last mess I made, basically I'm summarizing a relationship that's happening here. And it's all about the coefficients. It's also about the variables. We'll get to those eventually. But I'm seeing a pattern that's taking place. And again, even though I don't have it here, we could definitely write it in. Let's do an x plus y to the fourth. I would know the coefficients. Now, I would actually know the other values too, but let's put these in for now. It'd go 1, 4, 6, 4, and 1. And if I wanted to know out to the fifth power, it would go 1, 5, 10, 10, 5, and 1. And each time what's happening is, again, we're using the numbers above it to add to obtain those values. It's a very cool little pyramid, actually. So this connects us to Pascal's pyramid. This is often called Pascal's triangle or Pascal's pyramid. Now, it just looks like a cool shape, and yet, do you see those numbers that I've been writing over and over again? There they are. And each of these rows represents those coefficients of that expanded term. What I'm trying to tell you is that actually we can find some very complex multiplication values with very minimal work because of this beautiful pyramid. And in every case, you guys, the number is made by adding the two that are kind of above it in terms of that cycle, no matter where you are in that group. That's how you obtain those numbers. So this is going to help us to do some cool multiplication quickly. Watch the tricks. So let me show you some of my tricks. Trick 1. The coefficients are found here. So if I was expanding this one out, it would be a 1 here, and then it would be a 4, and then it would be a 6, and it would be a 4, and it would be a 1. The next trick is that you were to have watched a pattern in the values, the variables, that this one would always be the maximum degree in x. And then what actually happened is each term down, x decreased as we went, until there were none in the last term. The other thing you would have noticed is that y was at its maximum in this term, and it decreased each time. And so actually, there is the expansion right there. Now let's just go over that because that was kind of quick on you. So to the fourth power, I get x to the fourth, and I get y to the fourth. That makes sense. And then each time the x value is going down until I have none. Here, y start at 4, 3, 2, 1, and then none. The other thing to notice, and let me put a 1 there, I want you to notice that the degree is 4, 4, 4, 4. There's a 1 there, 4, and 4. Now watch. I'm going to do the whole thing from scratch here, 4 to the fifth power. I'm going to write small here, but I'd go 1, x to the fifth. Now my next number is a 5. It would go x to the fourth, y to the 1. Next, my number is a 10. X to the 3, y to the 2. My next number is again a 10. 10, x squared, y to the third. My next number is a 5, x, y to the fourth. And then finally, it is 1, y to the fifth. Whoa, I was able to do that whole thing just without doing a single bit of multiplication. Let's go through that. So notice 5, 5, add to 5, add to 5, add to 5, add to 5. And that last guy is also a 5, isn't it? The other thing I want you to notice is I got my values off my beautiful little Pascal's chart. Whew, now this last guy, I'm going to need some space, and it's not going to be pretty, but I think let's do it anyways. Let's give it a shot. Actually, if I zoom in, we'll be fine, won't we? Let's do it that way. So let's go down here and look at our values. Here they are. So let's do it. This will be 1, x to the 6. No problem. Next number, 6, x to the 5, y to the 1. Next number, 15. What do we got? X to the fourth, y squared. Okay, let's pull it over. Next number will be, what do we got next? 15, then it goes to 20. Then it will go x3, y3. Next number is a 15, x squared, y to the 4th. How easy is this now? Looks pretty tricky, but it's pretty simple. Let's go down. So after 15, we go back to 6. 6x, y to the 5, and then 1y to the 6. Cool, isn't it? Let's go through this. A 6, there it is. This turned out to be 6, 6, 6. All of those will always sum out to be 6s. There's some more of those. 6 and 6 and 6. And again, we see how that kind of, creeps into there as it shrinks into each of those spots. So I'm actually able to do something that just seems overwhelming. X plus y to the 6th power. I'm able to expand that thing out in a pretty quick way. Now, let's take a look at how we apply that. So what we add to this is we don't usually expand x plus y to the 3rd. We do like x plus 2. So you expand it out like you've just learned. We would fill out all of the blanks as if it was the generic one, x plus y. But the truth is our y in this case, that back term, is a 2. So wherever there's a y in there, we're going to plug it in. And then eventually that just simplifies. So you'll notice that 3 times 2 becomes 6. The 4 times 3 became 12. And 2 times 2 times 2 is 8. So we don't expect any y values, because if we have x plus 2 to the 3rd power, it should only have x's in it, and there it is. That's a nice way to expand that out. So if the generic expansion looks like this, and you and I are actually expanding x plus 2 to the 4th, what that ultimately means is wherever there's a y, we're going to drop a 2. So it would look like this. 1x to the 4th, 4x to the 3rd, and y to the 1. So we're going to drop a 2 there. 6x squared, y squared, which would be 2 squared. 4x, y cubed, 2 cubed. And then 1y to the 4th. So let's do the simplification of that. That would be, the final result would be 1x to the 4, 8x third, 24x squared. 8 times 4 is 32 x's, and 2 times 2 times 2 is 16. This would be the expansion of x plus 2 to the 4th. Pretty quick and sweet, isn't it? Okay, here's the generic expansion of x plus y squared. Not a very big expansion. But I did this mostly because I want you to notice that something changed. You see how that's 2x there and the minus 5? What that actually means then is I'm going to put in the 2x anytime I see x, and I'm going to put in that negative 5 where I see the y. So watch my pattern here. So it normally would go 1x squared, so that's 2 squared. 2 times x, that's 2x, times y, which is minus 5. And then 1y squared. Do you see what I've done there? I have placed in 2x wherever the x's were, and I put in the negative 5 wherever the y's were because of the change out here. So my answer would be 4x squared minus 20x's plus 25. So that's what that is. We know how to expand that. But I wanted to do a simple one so you can, before we get to some trickier guys with this. One more. All right. Here's the generic expansion that we learned using Pascal's triangle. Nice and easy. But that's just the generic one. We're interested in 2x's and plus 3. So that means wherever we see x, we're dropping in 2x's. Wherever we see y, we're dropping in a 3. Let's start that process here. Let's bring this in just a little bit tighter. So the first one is 1x cubed. That would be 2x cubed. 3x squared. That would be 2x squared. Y. And so we would put in a 3 there. The next one is 3 x's, That's just 2x. And then y squared. Y is a 3 here, y squared. All right, let's keep moving over. And then the last term is 1y cubed. Now, let's bring that a little smaller and let's finish it off. So how does this look? 2 times 2 times 2 is 8, so this is 8x cubed. 9 times 4 is 36x squared. 9 times 6 is 54 x's. And 2 times 2 times 2 is 27. Isn't that something else? We just did 2x plus 3 to the third power that quickly to get all of the values just right. This is binomial expansion.